Alright, welcome to my machine learning crash course with no math. This isn't sponsored by anyone, I just kind of felt like teaching a crash course in machine learning. So here we are. I do hold live lessons, usually every other Saturday or whenever I feel like putting together a lesson. But I decided to also record this stuff here for anyone who can't attend. Anyway, I'll just get right into it. So the goal here is to basically provide a crash course into machine learning with really not touching on math that much at all. And the reason I kind of want to do that is because I feel like that there's a lot of stigma around machine learning where you have to be very mathematically oriented and you need to know all the best and greatest mathematical equations out there, which is simply not the case anymore. There's such a wide selection of content out there for the average person with a bit of programming knowledge can just pick up and learn. And that's kind of what this is. Just a quick tutorial, or I guess a quick crash course composing of several lessons that just kind of go over machine learning. Without further ado, I will proceed. So I'm planning on having about 4, maybe 5 lessons in this crash course. The first one is what you are currently watching right now. I'll just briefly go over the course outline for this crash course. This first lesson is called Introduction to Machine Learning. And here we will go over the very broad terms and categories that you'll find a lot in the AI, world, as I could call it. We'll also go over some common tropes for the machine learning development cycle. So what steps you would actually take to develop a machine learning solution. And then I'll briefly mention some helpful tools for setting up your own machine learning environment. That will be lesson 1. Lesson 2 is when we'll chat about the actual theory and algorithms and concepts behind a lot of the commonly used algorithms that are available to you online to just quickly download and use. We'll go over how and break those down on a step-by-step level, how that stuff actually works. And again, I want to stress here, no math whatsoever. We're going to just use simple diagrams and speaking to you, teaching you how the algorithm actually works behind the scenes, and you don't really need to know the mathematical parts at this anymore. The reason why you don't really need to know much complex math anymore is because it's kind of like driving a car. That's kind of what developing machine learning solutions is kind of now. It's kind of like driving a car. Whereas, like, you don't need to know the inner workings of the engine and how the combustion works on on a scientific degree. You just need to know how to steer the wheel, park, reverse. That's it. That's all you really need to know. How to turn the ignition on. You don't need to know how the ignition actually works, because everyone already handled that for us. We have very smart people working at universities building this stuff for us, so we can just go along and drive the car or build ourselves a machine solution without needing to worry about all that fussy math stuff, because we already have a lot of good smart people doing all that work for us. But that's kind of so I guess from that perspective, I'll just be teaching you how to drive the car, how to use a machine learning algorithm, so how to import it into your program. I'll go over briefly like how it kind of works behind the scenes, so you have an understanding of how it works, and then you'll understand basically machine learning to all the extent you need to know without any math. Lesson 3 will be a continuation of that, so building on the theory from the previous class, learning more algorithms, which will be a very fun thing. And we'll also apply this theory and build our first machine learning model in the crash course. Lesson 4 will be theory focused more on neural networks. We'll chat about the different types of them and the concepts behind neural networks. And lesson 5, if this crash course gets enough interest, then it will be up to you guys out there. I guess tickles your fancy, whatever feels good. Maybe maybe we'll dive more into neural networks or something more fringe that we didn't really cover that much in the crash course. Anyway, we will proceed with lesson 1. So, this is the AI umbrella. So, there are 3 circles here that you can see, and I'll explain this stuff. Number 1 is like, what is artificial intelligence? This diagram here explains it pretty well. A very broad, very fundamental aspect of AI, and this is what this whole crash course is about, just understanding the fundamentals behind machine learning. If you understand that, you can go anywhere with this stuff. AI is fundamentally just a technique which enables machines to mimic human behavior. That's it. That is technically AI. Anything that is meant to pretend to be a human or mimic how a human should act or behave in any way, that is AI. That could be maybe as simple as, a video game AI, which we already call those ones AI, or it could be more like really anything, honestly. Anything that involves a computer that can try and mimic a human. That is quite a very broad topic, so we can delve further into a specific subset of AI, which is machine learning. And machine learning is the same thing as AI, where it enables machines to mimic human behavior, but it has the added benefit of the program being able to learn as time goes on. So it's mimicking human behavior, and it's also improving itself and learning as time goes on, and as it continues to mimic human behavior, it will learn new things. Maybe it should act this way instead of the way it was before, and it will just continue learning and evolving itself to be more and more human-like, or more and more better at its specific task. That is all machine learning is. Acting like a human, but with that added component that it will self-improve as time goes on. Deep learning is just like machine learning. It mimics human behavior. It has a learning component where it will improve with time. But deep learning is different in that deep learning tries to mimic the neurons inside the human brain. I'm not going to get too much into biology, but how neurons basically work, from my understanding, is you have a bunch in your brain, and then they fire off. They'll send pulses to each other. And that's how thinking works on a very, very basic and fundamental level. So that's what deep learning is, trying to mimic human behavior on the fundamental neuron level of the human brain, trying to mimic that. And that is what all these 3 different types of AI is, basically. You have AI, machine learning, and deep learning. So, we are looking specifically at machine learning, and even more specifically, these 2 white circles up here. Supervised learning and unsupervised learning. These are 2 different types of machine learning, which again is just mimicking human behavior, but with the learning components where the software will improve. So by that logic, unsupervised learning and supervised learning are just 2 different ways that we can program our machine learning software to learn. We can teach it to learn through unsupervised means, like clustering or dimensionality reduction, or we can teach it to learn through through supervised learning, such as classification or regression. And these are all different categories of algorithms. And let me go to the next page. to explain what I actually mean by an algorithm, because when I was learning this, I didn't really know what the word algorithm meant, which now looking back on it's absolutely silly. I don't know why anyone could not explain this to me easier before. But the fundamentals of machine learning is that, first and foremost, a machine learning algorithm is just different ways of identifying patterns in data. Now that sentence might be a bit confusing because of the word algorithm, so let me explain that. An algorithm is simply just a step-by-step procedure to follow, like a baking recipe or like a step-by-step tutorial. You know, like if you're watching a YouTube video on a tutorial on how to, I don't know, bake a cake, or even if you're just reading a recipe on how to bake a cake, you know, get your eggs, get your flour, mix it all together, maybe add some milk or water, stuff like that. Step-by-step process. That's an algorithm. Those words, recipe and algorithm, they're interchangeable. They mean the exact same thing. So when I say that all machine learning algorithms are first and foremost just different ways of identifying patterns in data, all that means is we have different procedures or different steps that our software will try to identify patterns. That's it. Every single machine learning algorithm is fundamentally that. It's just you're sending some data into your software and it tries to find a pattern. And there's different ways to try and find patterns. And those different ways are the different algorithms. Like there's different baking recipes for cakes. You can have, there's probably a dozen different ways to bake a cake. There's a dozen different ways to find patterns in data. That is what an algorithm is. And that is what these different algorithms are, unsupervised and supervised learning. They're like two different ways to bake a cake. And yeah, they'll come out a little bit differently, but more or less they do the same thing, which is identifying a pattern. Once you understand those fundamentals, this becomes a whole lot easier. So we will break down these two things at the top here, unsupervised and supervised. We'll start with supervised learning. So, supervised learning, and again I'm going to take it back again, this is just a step-by-step process on how to teach your computer how to identify a pattern. That's it. This is just a way for your computer to identify a pattern in the data that you present it. That's it. And we call this one supervised learning. Supervised learning is composed of two different pieces. You have your input data, and then you have labels that are associated with that input data. This image here kind of shows what I mean a bit. Let's say we had our computer, and we fed it a bunch of images of apples. Now, the computer, that's all well, good, and fine. It can look at the images and look at the colors on the pixels of the image. But then we also give it labels. We tell the computer, this is what they are. These are apples. So it will look at the image. It's kind of like a flashcard. Like, you know, if there's a question on one side of the flashcard, and then the answer is on the other side. That is the exact same way that we are teaching this program to learn. By giving it a flashcard with the question, and then it flips the card and then reads the answer on the back. And that answer on the back you can think of as the labels, or the annotations in this image here. Same thing. And that is it. That is supervised learning. We're giving the answer and the question. In this case, the question is an image of an apple, and then we feed that into our algorithm, and it learns it, and then there we go. You can think of that as the study session. You know, whenever you're preparing for a test, you would study. You know, you read your flashcards and everything to train yourself and learn how to, you know, answer the questions. And then you have the test, or the final exam. And that final exam is this apple right here with the question mark. So after the model has done a good job studying and learning and training itself to recognize what is an apple, you will give it an image. But Sorry, my throat is starting to die. Okay, you will give it an image, but you will not tell the computer what that image is. And it has to guess if it is an apple or not. And how does it know that? Based on that studying session beforehand, where you gave it the flashcards, apple on one side, and then the actual image of the apple on the... I got that mixed around, but you know what I mean. Yeah, that is entirely what supervised learning is on a fundamental level. It is given input information, and it tries to guess the label based on that input. That is entirely supervised learning. Now let's go to unsupervised learning. And it's pretty similar with just one slight change. That one slight change means a lot, but it's a very simple change to understand. Unsupervised learning is the same exact thing as this previous image, but rather than give the answer during the studying session or this training session, in machine learning we call that we divide the data between training and testing. So instead of giving the label alongside the training data or the studying session, we don't give the model any clear right or wrong answer. We don't tell them what the right answer is. It's like if they saw the image of the apple in the flashcard, flipped it on the back, flipped it over, and there was no answer there at all. It's just simply given these images, and then it has to do something with it. So you might be wondering what is it supposed to do? It doesn't know right from wrong. Exactly. That is the exact point of unsupervised learning, to not actually know right from wrong, because these are questions that you, the developer, might not actually know. What is the correct answer, or what is the wrong answer? You don't know right from wrong, so how is the model supposed to know right from wrong? And that's the beauty of unsupervised learning, is you can actually learn stuff from the machine learning model. Because remember, fundamentally, every machine learning algorithm is just trying to identify a pattern. So when you give it this information, like maybe these images of apples or watermelons, and you don't tell it right from wrong, this algorithm will try and group and still try and find patterns in the data with no inherent knowledge of right or wrong. And that stuff is pretty powerful, but it's also a bit confusing to understand why you would do this, which is why I made a lovely second page to do this. So with unsupervised learning, there is no right or wrong answer at all. It's not black or white. The goal with unsupervised learning is to actually draw inferences from the data that you yourself might not actually be aware of. Its best use cases are when you're actually trying to find patterns in your data, but you don't know exactly what you're looking for. This is a good image here. If we just have this jumble of images, we got some triangles, some squares, some circles. We feed that into our algorithm, and again, every algorithm is just trying to find patterns and group stuff. So the output, it does a fairly good job of grouping this data. So you can apply this to anything, really. If you maybe have customer information and you want to maybe find who are your best customers, you can feed in some information like let's say you record information of every customer that comes in, like how much money they spend, how often they come in, if they use any discount codes or anything. You feed all that data into your system, and it will try its best to group that data based on what it sees fit. And that's the power of that, because since it doesn't know right from wrong, it will just do its best to try and group the data. And since it does that, you can draw some really powerful interpretations or inferences from this data. It might help you find the best customers that you should target more with your advertising, because these people seem to like to spend a lot of money at your place, and you didn't really know what makes a good customer. So you just send in all this data, and this algorithm finds you your best customers, who then you can go and target with advertisements or give good deals and whatnot. That is unsupervised learning. Good job. So supervised and unsupervised. Perfect. So now we're going to talk about these outer circles, the clustering, the dimensionality, the classification, and regression. These are, again, further levels of unsupervised and supervised learning. But hopefully you understand what unsupervised and supervised mean. You can, since this is a video, you can go back and rewatch those parts to learn it a bit more if you need to do so. So, there are two different types of algorithms that are supervised. Now, if you remember, supervised learning is you give the question and the answer to the computer at the same time. So, well, that is what supervised learning is. And now we're going to divide that up into two different types, and they're pretty simple types. The names might sound a bit scary, but they're not at all, trust me. Classification is just you giving the data to the model, and it tries to predict a textual response. It tries to predict like a category or like some kind of English or text response. Regression is when you are training the model with the data, and then it tries to predict a numerical result based on its training. That's it. There are different algorithms for these two different kinds of problems, but that is fundamentally what they are. Classification is you're trying to predict a English, like a word answer, and regression is you're trying to predict a numerical answer. Numerical answer could maybe be like trying to predict a stock price or trying to predict your sales revenue for the next quarter or something like that. Classification is kind of like this image right here, trying to predict if something is a cat or a dog. A text response. Are they a cat or are they a dog? So English words. That is what two different types of supervised learning is. And there are tons of different classification algorithms and tons of regression algorithms. There are just multiple ways of doing these two kinds of things. Unsupervised learning is mainly this thing on the left, but the one on the right does play a pretty big role. Most unsupervised, which again is there's no right or wrong answer. The algorithm is simply trying to identify patterns in the data with no idea of right or wrong. Is called clustering. And it's pretty straightforward from this image here. Let's say we had this data set on the left side, and then after we run it through the model, you can see that this model identified 3 different clusters, or 3 different groups in the data that might be of significance. And here's a little fun trick, is when you're looking at this thing on the left side, you're already probably in your mind dividing up these things into 3 different groups. But there's nothing telling you that these should be 3 groups at all besides just their closeness, right? Like there's nothing on the x-axis or the y-axis that's telling you this is that and this is the other. Your brain is already doing unsupervised learning. It's already grouping this stuff into 3 different groups. And we are simply just trying to imitate that human behavior like so, creating 3 different clusters. Except instead of us doing that, we want a computer to do that. And there are dozens of different algorithms or dozens of different recipes to do stuff like that. Dimensionality reduction. Gonna take a quick swig of water. So, dimensionality reduction. This is quite a big part of machine learning, especially deep learning, or just big data in general. When you're dealing with a lot of data, it can be hard and taxing to actually process all that data and actually train a machine learning program. Just because of the sheer amount of data, stuff doesn't really work that well. It might, some pieces of data might get overshadowed by other pieces of data. There simply might just be way too much of it, that it would take like years upon years to even train your model. So we wanted to fix to that. And dimensionality reduction is one of those fixes. It's pretty straightforward. You can think of dimensionality reduction is reducing the amount of data being processed, but still having the underlying meaning of the data behind it. You can think of this as kind of like a zip file, for example. You know, like a zip file, if you ever had to try and send something over the internet, compresses the data. It like compresses your files. And what that does is it actually reduces the amount of data inside of your files. But it doesn't reduce it to the extent that you cannot, that's irretrievable. That's why when you unzip the file, it's kind of like expanding the data. There's enough data there that when you unzip the file, it can still draw its own inferences and understand what these files are, even though they were reduced in size. So that makes it easier to send and to process, and yet, even though they've been compressed and the data has been reduced, the inherent meaning underneath is still there. And that's kind of what dimensionality reduction is. Reducing the amount of data, but still keeping the underlying meaning behind the data present, so it can still be used. Another idea here is on the right side. You can think of this in like two different views or two different dimensions. When you play Mario, you're playing a two-dimensional game. So you see the pipe, you see that little monster jumping out of the pipe, and you see Mario. But what Mario sees, because he doesn't live from our perspective, he doesn't see this 2D world. He lives in a little one-dimensional world. So this image on the bottom is actually what Mario sees. So the data that Mario has is drastically reduced, and yet there is still the inherent meaning behind it. You can still see the pipe of like in front of Mario's face, so he knows that there's something there. And you can still see the monster, you can still see the red from the monster. So even though the data has been drastically reduced for Mario, he can still draw an understanding of the world around him. And that is what dimensionality reduction is. Alright, so that was the end of the theory session for this first lesson. Now we're going to chat about the machine learning development cycle. And there's about 5 steps or so. They're pretty straightforward as well. Nothing really complex to understand here. First step, when you're developing a machine learning solution, you're going to want to identify goals. So what exactly is the problem that you're trying to solve? Should we even use a machine learning approach to solve this problem? Next step is your research and exploratory data analysis. In this phase of development, you want to see what data you actually have access to. So what are the various data sources? Am I working with databases? Am I going to be doing some web scraping? Where exactly will I be getting my data from? And the second part of that is, what is the quality of my data? So once you identify where you're getting all your data from, you want to do a bit of exploration, pick it apart and see if there's any issues with the quality. You would want to look for is there any redundant data that maybe would just take up space and it's not really that valuable? Or maybe is there important data that's missing? and you think if that data is missing, your machine learning software isn't really going to perform that well. So that's the research and exploratory data analysis portion. 3 is when you actually design your model. So you'll decide based on what your problem statement is and what data you have access to. You'll decide which machine learning algorithms to actually build. And it's always good to design a few so you can compare the results against each other. You will also have to determine the data format required to run your models. An example could be if you're writing a image processing algorithm, you're going to need images, and those images might need to be modified slightly to be properly fed into your model. And the third step there is to tweak and fine-tune some algorithm parameters to conform to your needs. So when you'll be using stuff in this crash course, you're not really going to build any machine learning algorithms from scratch. They will have all been made by some really smart computer scientists at some universities. So you'll just import those into your Python file, maybe change around some parameters so that they, tweak them a bit so that they work better with your needs, and just go ahead with them. That leads us into step 4, where you execute and test the results. You execute the model, and then you measure the results, basically. Since you would have made multiple machine learning models, you can compare them against each other and see which ones did good and bad, and why you think that from a developer perspective. And you can end off with any future recommendations or closing thoughts. This entire process, it can usually be written in like some kind of research report from step 1 to 5. That's it. That's the entire development cycle for a machine learning developer, or engineer if you want to be cool. Setting up your environment. Here's just a couple things off the top of my head that I felt would be pretty helpful. Python for starters. Reason for Python is there is an absolute plethora of machine learning content out there for you to use. So I really recommend Python as well as Jupyter Notebook, as it just makes development a heck of a lot easier. Machine learning libraries. This is the main meat of the crash course, and this is where we'll be using a lot of these libraries. I think TensorFlow is one of the more well-known ones. There's also Keras and scikit-learn, which the latter I'm more familiar with. And I think we'll probably be using that moving forward. They just contain a bunch of content for you to build your own machine learning algorithms. They have everything from supervised learning to unsupervised learning, classification, regression, clustering. It's all jam-packed in those libraries that you can use to your heart's content. I also recommend some libraries for actually handling your data, so like reading it into your file and making any processing or changes. I recommend Pandas or NumPy, or NumPy. I used to call it NumPy for a while until someone else said it, then I realized it sounds a bit dumb the way I'm saying it. So I'm going to call it NumPy from now on. Yeah, I recommend looking into all of these in your spare time whenever you have time. And that was the end of lesson 1. If you have any questions, hopefully you know how to reach out to me. And thank you for coming. I'll be having lesson 2 up shortly.